And next we want to do is that we want to make a small surgery on this unimodular lattice lambda. And I should quote this surgery because surgery itself is a terminology in mathematics, in topology. The surgery is the following. We define W to be the orthogonal complement of the line through the B sub 1. And we consider the following new lattice. Lambda sub W to be the projection of lambda onto W. So here, pi sub W is a projection from RD to W. So this is a projection along the line through B sub 1. So now let's draw a picture of this projection in a three-dimensional case. This plane is W, and B1 is orthogonal to this plane because W is defined to be the orthogonal complement of B1. And there will be B2 and B3. Here's B2 and here's B3, say. And now what you do is that you project B2 and B3 onto W. Say this is B2 prime and this projection image is B3 prime. And you know from your calculus or linear algebra class that B2 prime can be written as B2 minus some coefficients times B1. And this coefficient is the inner product of B2 with the normalized vector along B1. So this is a projection of B2 along the direction B1. And you similarly can do it for B3, B4, etc. And now we do the projection for all B sub 2 through B sub D. You get the projection images B sub 2 prime dot through B sub D prime. And you can show they are linear independent. Indeed, if you add coefficients lambda 2 all the way through lambda D and let this equal to 0, this gives you, by using the formula here, that lambda 2 B2 plus the lambda D BD without primes plus some coefficients times B1. So we are using this part equals to 0. But you know from the beginning that B1, B2 through BD are all linearly independent. So you will get from the linear independence of B1, B2 through BD that lambda 2 through lambda D are all 0. So after projecting those vectors down onto W, you still get a linear independent set. Now as a result, lambda sub W, which is a projection of the original lambda under the projection along B1, becomes a z-span of B2 prime all the way through BD prime. And we note that at this point, we don't know lambda W is a unimodular or not. Although lambda is unimodular, we don't know what kind of co-volume lambda sub W will have. But we will have the following estimate. Because lambda is unimodular, and B1, B2, all the way through BD is a basis for lambda. We know that if you take the wedge product as a norm, this will be the same as the covolume of lambda, which is 1, because lambda is unimodular. Now, you might be curious how this norm is defined. This norm is defined as follows. Remember, when you take the D wedge product of RD, you just get a one-dimensional space. And this one-dimensional space only has one basis, E1 through ED. The wedge product of E1 through ED. And in this wedge product space, you stipulate that this norm, this guy, has norm 1. And as a result, when you take this norm of the wedge product of B1 through BD, you just get the determinant. This will be just the determinant of the matrix formed by B1 through BD as column vectors. The absolute value of this determinant, which by our definition of unimodular lattice is equal to 1. And now let's further study this norm. You know that when you project those B2 through BD down, you do not change this wedge product. Let's first replace B2 with B2 prime. B3 is still the same all the way through BD. You know those two wedge products are the same because B1 and B2 are orthogonal. Because you can decompose B2 as the sum of some linear multiple, some scalar multiple of B1 plus B2 prime. And this part in particular is linearly dependent on B1. So as a result, when you replace B2 by B2 prime, you do not change the wedge product. And furthermore, you continue this replacement, and finally you got B1 wedge B2 prime all the way through BD prime. But you know at this point that B1 is orthogonal to the linear space spanned by those vectors, which is W. So you know that this guy will be same as the norm of B1 times the norm of the rest. Now, how is this norm of D-1 wedge product of D-1 vector defined? So this is defined because this time you are taking the D-1 wedge product of RD. This time this guy is spanned by the vectors. This guy, it is spanned by the vectors E sub I1 all the way through E sub I d minus 1, where each index I sub j is between 1 and d. So I sub j is between 1 and d. And this norm, the norm on this, is induced by the inner product on it. The inner product on this space is defined through, if you are taking I1 all the way through E sub ij, E sub I d minus 1, and E sub j1, which all the way through E sub j d minus 1. This will be the chronic delta of, if you consider pairs, I1 through E sub I d minus 1 and j1 through d sub j minus 1. And here you also stipulate that I1 through ID, j1 through jd, I1 through ID minus 1, j1 through jd minus 1 are all in the increasing order, strictly increasing order, otherwise it will be 0. And this inner product will be the chronic delta, which takes on the value 0 and 1. It is 1 if this I1 through d minus 1 and j1 through jd minus 1 is 1, otherwise it will be 0. And you expand this linearly to this space. That gives you the definition of the inner product on this space, and which induces a norm on it. And you might also be curious about how this is obtained. So this is given by some basic linear algebra, but let me write a quick proof anyway. So, this guy is a determinant of the matrix formed by those vectors. If you look at the determinant, and let's take the square of this determinant. The square of this determinant will be the same as the determinant of the transpose of this matrix times the determinant of this matrix, which if you write this out explicitly, you will see immediately that this will be the same as the Gram matrix. First you get B1, the inner product of B1 comma B1. So next one you will have B2 prime comma B1 inner product. BD prime comma B1 inner product. Here it should be B1 comma BD prime. In the lower right you have BD comma BD prime comma BD prime. And you know that those guys are all zeros. So you will get B1 comma B1. So all 0. And you will also get 0 in here because the matrix is symmetric. But here you will get the Gram matrix of B2 prime through BD prime. So in the end, you get the norm square of B1 times the determinant of this matrix formed by B2 prime through BD prime squared. And now you take the square root of both sides. You'll get this. I know I have spent lots of time only to prove one result that seems to be trivial to some of you. That is, that 1, which is the norm of this guy, is equal to the product of those two norms, which follows simply from the fact that B1 is orthogonal to the plane, to the space spanned by those d-1 vectors. That should be trivial to some of you. But anyway, what is the significance of this? The significance of this is that if you look at the co-volume of lambda w, which is the determinant, the absolute value of the determinant of B2, the matrix formed by B2 prime through BD prime. Which is the norm of the wedge product of those guys, which is 1 over the norm of B1. But you know this is bounded below by S and bounded above by some constant that only depends on D. Remember, we call this CD bar. So the reciprocal of this is bounded below by 1 over CD bar and above by 1 over S. What this tells you is that after rescaling by a bounded scalar, we may assume that the lattice lambda sub w is unimodular. That's the significance of this whole process of bounding this guy by two constants. And I should emphasize that the price we pay for rescaling is that the length of vectors B2 prime through BD prime are scaled by a constant that only depends on D and S. This part is the most important part. The length of the vectors are only scaled by a constant that only depends on D and S. We don't really care D and S because S is fixed, D is fixed. That's good.